Humans have 10 fingers, and as a result, we count to the base 10. When we reach 9, we continue to 1 10 and 0 units, instead of using another character for 10. For example, 2,684 is represented by 2 thousands, 6 hundreds, 8 tens, and 4 ones. We've always been taught arithmetic using the base 10, and so it seems natural to us. However, there's nothing special about the base 10. Indeed, when telling the time, we use base 12 or the duodecimal system. Plus, 12 has advantages over 10 because it's divisible by 2, 3, and 4. Computers are made from electronic switches that are either off or on, 0 or 1. All modern digital computers therefore use binary numbers internally. Binary numbers only have the characters 0 and 1. It's perfectly easy to do arithmetic in binary using the exact same process we use in decimal, just remembering that the number above 1 is 1 0, meaning 1 2 and 0 ones. When computers display numbers, they are converted to other bases for the benefits of humans. Internally, all numbers are binary. We call the characters of a binary number bits. The word bit comes from shortening the phrase binary digit. Just as a decimal number of n digits can represent 10 to the power of n possible numbers starting at 0, a binary number of n bits can represent 2 to the power of n possible numbers starting at 0. IPv4 computer addresses have 32 bits. 2 to the power of 32 is more than 4 billion. To be precise, I think it's 4,294,967,296 units. We will also be discussing Mac computer addresses, and these have 48 bits. 2 to the power of 48 is more than 256 million. Whereas an IPv6 address has 128 bits, and that allows for more than 256 trillion unique IP addresses. Now, a long string of binary numbers is very difficult for humans to read. One technique to make them more tractable is to break them into groups of 4 bits called nibbles. Each nibble represents 16 possible values from 0 to 15. So if we break a binary number into groups of 4 bits, then each group can be represented by a hexadecimal digit. To write a hexadecimal number, we need 16 digits. By convention, we use the existing digits 0 to 9, and then we add characters A to F to reach 15. So 1111 binary is the same as 15 decimal, and the same as F in hexadecimal. Let's try adding the two hexadecimal numbers DEAD and CAFE. Adding E and D hexadecimal is the same as adding 14 and 13 decimal and equals 27 decimal. 27 decimal is 116 plus 11 units. 11 is represented in hexadecimal as B, so we write down the B and carry the 1. Pause the video to go through the steps in this addition and see if you can figure it out for yourself. Okay, with that in mind, here's another example, this time without the prompts. Pause the video and try it yourself to see how you get on. In the next slide, I'll show you the fully worked out results. And here they are. When it's manufactured, every device that connects to a network is assigned a Media Access Control or MAC address. MAC addresses are 48 bits long and are displayed as 12 hexadecimal digits. This MAC address is guaranteed to be unique for the entire world. No other piece of equipment will have that specific MAC address. This uniqueness is achieved by assigning blocks of MAC addresses to manufacturers. Each manufacturer must then use these numbers carefully so that no two devices are manufactured with the same MAC address. If you know the MAC address of your device, you can use a website such as macvendors.com to find out who the manufacturer is. IPv4 addresses are based on 32 bits. These bits are grouped into 4 8-bit groups called bytes. Each byte is displayed as a decimal number with a dot between each decimal number. This hybrid number system is called dotted decimal notation. Those IP addresses are then broken into 2 parts. One part to the left is called the network ID, and the other part to the right is called the host ID. This is similar to the case of MAC addresses divided into a manufacturer prefix and a unique postfix. Dividing IP addresses into 2 parts is called subnetting. The location of the divide between the network ID and the host ID is set by the network designer. In the IPv4 example below, the divide is 25 bits for network ID and 7 bits for host ID. In this example, subnetting is not aligned to the byte boundary. Subnetting is described using either a prefix length, the number of bits in the network ID, or it can be written as a subnet mask. This is a dotted decimal notation that represents an address with the bits set to 1 for the network ID and the bits set to 0 for the host ID. Now, back when IPv4 was originally developed, it was believed that more than 4 billion addresses was more than enough. But that works out at less than 1 address per person nowadays. To help alleviate this scarcity, 3 address ranges were set aside for private networks. These ranges are referred to as RFC 1918 private IPv4 addresses. The same RFC 1918 address ranges can be used over and over again within different CloudKix projects. Another range of addresses, referred to as link local addresses or RFC 3927 addresses, are used to implement Cloud Init functions in CloudKix. This leads us on to IPv6, which was developed to overcome the IP address exhaustion of IPv4. With 128 bits, there are trillions of trillions of trillions of possible addresses available. IPv6 addresses are divided into 8 groups of 16 bits, and each group is displayed as 4 hexadecimal digits, sometimes called words. The groups, or words, are separated by the colon symbol. CloudKix operates within a /32 subnet. 2A02:2078:/32. Each region within CloudKix has a /48 allocated to it from within the /32 subnet. When you create a project within CloudKix, you are allocated a /64 from within the /48 allocation to the region on which you built that project. This means you have close to 2 trillion IPv6 addresses available to each project you build. I'm hoping that's enough. A final point to note, IPv6 addresses are 128 bits long, so even when written in hexadecimal notation, that makes them very long to write down. To make them easier to notate, you're allowed to strip any leading zeros in any word, and you're allowed to replace the longest continuous range of words comprising of zeros with a double colon. These 2 rules do not create any ambiguity in interpreting the IPv6 address, but make it much easier to notate and read them as humans. That's all for today. Thanks for watching.